Consider a simple animation of sunrise. We can clearly see that a majority of this picture is consisted of the landscape, which does not change over multiple frames in both shape, size and color. This means that this data is redundant over the entire duration of the video, and the video could have been easily compressed just by observing the motion of the sun. If there was a way to just convert the motion of the sun into data that can be stored instead of pixel data, we can easily compress this video. This is where block matching and motion estimation comes into the picture. In our project, we have performed motion estimation, or the act of determining the motion of an object on the frame using an algorithm called as block matching. You can see the overall setup which has been implemented here. We have written the code on Vivado, which is a program offered by Xilinx Incorporated. The program is running on an FPGA. On the 7-segment display, you can observe that the 1F13 is the final endpoint that is being calculated by the algorithm. This is the video display output from the FPGA.
Now I will explain block matching algorithm. As you can see, these are the two consecutive frames of a video. These are two 96 cross 96 pixel images. We have divided the whole image into several macro blocks of size 16 cross 16, and we iterate over each macro block and perform some action. Suppose this is the macro block on which we are iterating. So corresponding to this macro block in the second frame, we make a search area which is slightly bigger than this macro block. So as you can see, the size of the macro block is 16 cross 16, and the search area, which is shown by green color, we have taken it of around 48 cross 48 pixels. Now in the main algorithm, we place this macro block here and we find the best possible match for the macro block. We calculate the sum of absolute differences by placing it here. First we'll place this macro block here, then we'll move one pixel, and then we'll place it here and calculate the sum of absolute differences and figure out, and then we will figure out the best match, which will be the endpoint for this start point. So the start point of the vector will be here, and the endpoint will be the best match of this macro block in this second frame.
Let me now explain the expression that we have used to determine the smallest error between two different macro blocks in our search area. First, we define a quantity called the SAD, or the sum of absolute differences for each macro block, which is defined as the sum of the absolute differences of each pixel value between the two macro blocks in comparison. Now, the SAD consists of three components: the red component, the green component, and the blue component, corresponding to the R, G, and B values of each pixel. To compute the SAD between two pixels or two blocks, we first find the absolute difference of the red values, absolute difference of the green values, and absolute difference of the blue values, and sum them up for each of the pixels in that block corresponding to the pixels in the search block. This is a flowchart of how we've approached the problem of motion estimation on an FPGA. Initially, we convert a PNG file consisting of a 96 cross 96 pixel image into a coefficient file which can be easily loaded into a BRAM, or the block RAM of an FPGA. This is done using a Python script which stores all of the individual pixel values in the form of a linear matrix, and each address having the red, green, and blue values of the pixel in a binary format. After loading the image into the block RAM and creating 3 instances of the same, we now use 4 major blocks to execute our entire program. The first and the lowermost block is the sum of absolute differences calculator, which calculates the sum of absolute differences for two different macro blocks defined by its initial address. Once the sum of absolute differences is calculated, the finite state machines associated with both of these blocks instructs the minimum error block to perform its function. The minimum error block supplies the starting value of each block that needs to be compared within a given search area. The block then compares each value and determines the closest matching block or the block with the least amount of error and writes the location of the center of that macro block to memory, that is, block RAM. A higher block then instructs this entire two block setup of minimum error calculation and sum of absolute differences to move between different search areas within the entire image. Once every block has recursively performed its function, we notice the value on the VGA display, which is handled by a different block. The VGA block either displays the picture on the screen or writes the endpoints of the vectors into memory. It is important to note that reading and writing do not happen simultaneously in order to prevent race like conditions.
This is the display output on VGA which is coming from FPGA. Now here you can see these are the two consecutive frames of a video. Now here it is noticeable that in the second frame the whole image has been shifted diagonally up. So you can see the gap here and the gap here. So the whole image has been shifted diagonally up. Now we have divided the second frame into macro blocks of size 16 cross 16 pixels. So here and the image size is 96 cross 96 pixel. So there are 36 macro blocks and these black dots represent the center points of one macro block. Now the white dots represent the motion vector. So here since the image has been shifted diagonally up, so the motion vector which is expected is like this. The motion vector should be diagonally up. Now here let's take this macro block. So this macro block has a start point here and it has an end point here, which means that this block has moved here. So it shows the motion vector like this. Now this is the same for this macro block as well and this macro block as well. Now for these macro blocks also the output is diagonally up. In the bottom you can see that new objects are coming. So in this frame there is no orange dot, but in the second frame there is an orange dot, so a new object has come into this image. So here the efficiency of block matching algorithm reduces and here we are getting some disturbed output.
This is the power consumption analysis generated after FPGA. As you can see, the I/O consumes the most amount of power as the VGA port is constantly active. The next more power hungry operation is the BRAM operation, which is as expected.